Welcome to ASHRAE's Tech Hour. Today's subject is water, impacts on building occupants' health. Our presenter is Robert Bowcock, member of ASHRAE's Environmental Health Committee, licensed California Grade 5 water treatment operator, appointed to serve on several water master boards by California Superior Courts, provides expert witness testimony to state and federal courts, founder of Integrated Resource Management, LLC, an industrial water management services and environmental compliance services company. And now, Bob Bowcock.
Thank you for joining me today. Today we're going to talk about water and its impacts on building occupants' health. The agenda today will include the topics specifically focused on the source-to-tap approach. We're going to talk about quality dynamics, source seasonality, treatment, transmission and distribution, storage, supplemental treatment, and occupant use and exposure. I'd like to begin by discussing a concept of a community drinking water system. As regulated by the U.S. Environmental Protection Agency, for all buildings, regardless of their source, if the source is a community drinking water system. So drinking water systems can be broken down into at least three categories. First is the public water system, which can be run by a utility or a municipality. Individual water systems that are basically operated and regulated by states and local government, but can be for private property owners, or individual buildings can have their own water source and water supply. It too is a community drinking water system. And then ultimately, we break them down into non-community and community drinking water systems, and subcategories of transient and non-transient systems. A transient system would be the gas station, a park, a resort, a campground, or a restaurant that you might visit. Sometimes industrial complexes, private apartment buildings, motels, they can also have their own water systems. Non-transient would be a school, a factory, an office building, or a hospital that has a separate drinking water system. Or if supplemental treatment is taking place at a non-transient drinking water system, they are then considered community drinking water systems for the purposes of that activity of retreating the drinking water. Let's begin by talking about the quality dynamics. The water quality dynamics from the source are in three categories: physical, chemical, or biological. Physical characteristics are those that can be observed with the senses or measured with equipment related to physical state of water. Temperature. Temperature influences chemical reactions, the solubility of gases like dissolved oxygen, and the metabolic rates of aquatic organisms. Turbidity. Turbidity is measured in the cloudiness of water caused by suspended particles. High turbidity can interfere with light penetration and may indicate the presence of contaminants. Color, taste, and odor. They're aesthetic indicators that, while not always health concerns, can suggest the presence of organic matter, industrial pollutants, or other contaminants. Total dissolved solids, TDS, conductivity, they're measurements of concentrations of dissolved inorganic or organic substances, salts, minerals, metals. Conductivity is an indirect measurement of the concentration of these ions. And finally, total suspended solids. It's a mass measurement of the solid material larger than 2 microns that is suspended in the water. Next, we'll discuss chemical parameters. These are measurements of the various substances in dissolved or present in the water, which dictate its chemical composition. pH, or potential hydrogen, indicates the acidity or alkalinity of the water, which affects chemical reactions. Mineral solubility, and the effectiveness of water treatment processes. Dissolved oxygen, or DO, the amount of oxygen available in the water for aquatic life. Low dissolved oxygen levels often indicate organic pollution. Biological oxygen demand, or BOD, chemical oxygen demand, or COD, measures the amount of oxygen required to break down organic matter in the water, indicating the level of organic pollution from sources like sewage or industrial waste. Nutrients, nitrogen and phosphorus, while essential for life, excessive levels can lead to eutrophication and harmful algae blooms. Last year in North America, we experienced 22,000 recorded harmful or hazardous algae blooms. Hardness measures the concentration of dissolved calcium and magnesium ions. High hardness can scale in the pipes, but is generally not a health risk. However, this scale is the basic housing for biological activity in the future. Metals, trace elements like lead, mercury, arsenic, and cadmium can enter water bodies through industrial discharges or mining activities and are often toxic. Chlorine or chloramines are residual disinfectants used in treatment. They are monitored to ensure efficacy and avoided adverse health effects or taste and odor issues, but they too can present significant chemical water quality issues in building water systems. Organic contaminants, these include pesticides, herbicides, pharmaceuticals, and industrial pollutants. Most recently, many of us are hearing about the perfluorinated compounds associated with Teflon and Scotchgard. Those are really impacting water quality nationwide, if not worldwide. Finally, in this category, we'll talk about biological parameters involved in the assessment of living organisms and their activities, which help to determine the ecological health of a water body. Microorganisms, they include bacteria, for example, E. coli or fecal coliform, viruses, and protozoa. Their presence often indicates contamination from human or animal wastes. Algae, phytoplankton, they're essential to the food chain, but harmful algae blooms, HABs, can produce toxins and deplete oxygen. Microcystin is a common product of a hazardous algae bloom. And if a dog or another wild animal actually engage with that algae, the pustules will pop and will kill a large animal within minutes. It's basic component of neurotoxin and is used in warfare as biological toxins. It's very, very serious, and there is a rapid increase of these getting into water. And if they're in the source, they will pass through the treatment process and impact indoor building water quality. Aquatic microinvertebrates and fish, the presence or absence or abundance of certain species can serve as indicators of long-term water quality conditions. There are unfiltered sources of drinking water in the United States that actually have a microscopic brine ship that retains its presence in the water supply and can actually harbor smaller biofilm and dangerous bacteria within its shell structure. We also monitor these parameters for public health protection and environmental stewardship, often guided by standards and regulatory bodies like the Environmental Protection Agency or the World Health Organization. Now that we understand the characteristics of sources and the source complexity, we want to talk about source seasonality. Source water quality exhibits significant seasonality due to variations in weather, climate, and human activities throughout a year. These changes affect physical, chemical, and biological parameters, leading to different dominant water quality issues depending on the season. Seasonal variations in water quality require year-round monitoring to ensure safety and quality. Utilities adjust for treatment processes to manage these functions, which change building water quality. Let's start with winter, pipe stress and leaks. caused by freezing temperatures can cause water pipes to expand, contract, and potentially burst. Cracks can allow external contaminants, as examples, rust or soil, to enter the water supply lines. We also experience salt runoff. Salt and chemicals used for de-icing roads can seep into groundwater supplies, affecting private wells and public drinking water wells, causing a salty or metallic taste in water. Likewise, these chemicals run off the roads and parking lots into surface water supplies, having the same salty or metallic taste effect in the drinking water. These also impact the water treatment processes, changing the total dissolved solids and the total suspended solids. Dissolved oxygen levels are typically higher in winter due to lower water temperatures. All of these winter impacts significantly change water quality and the treatment processes deployed. Spring. As we reach spring, there's increased runoff. The melting of snow, heavy rains in the spring create significant surface runoff. This water picks up pollutants like dirt, sediment, organic debris, fertilizers, nitrogen and phosphorus, pesticides, and animal waste from urban and agricultural areas, carrying them into rivers, lakes, and groundwater supplies. Turbidity and odor, they influence the suspended solids, which increases the water turbidity, the cloudiness, and can often cause noticeable changes in the water's taste and odors. Let's move on to summer. Algae blooms, warmer weather temperatures, and increased sunlight can create ideal conditions for algae growth in reservoirs and lakes. Algae blooms can cause earthy or musty tastes and odors in tap water and affect water chemistry, sometimes leading to bacterial growth in untreated sources. Bacterial growth, warm temperatures, can increase bacterial reproduction rates in slow-moving pipes, private wells, or water storage tanks. Concentrated pollutants in some areas, less rainfall and lower water levels, low flow conditions in rivers and streams can concentrate pollutants and dissolve minerals, increasing issues like water hardness and electrical conductivity. Think of it as boiling a pot of water. As the water evaporates off, you begin to see the cloudy concentration of the minerals in the bottom of the pot. This is what occurs in our lakes, rivers, and streams, in our source water. Groundwater pumping stress occurs in summer months as well. Higher water demand for irrigation and public supply during summer can increase groundwater pumping, drawing down shallow, potentially contaminated groundwater with higher concentrations of contaminants like nitrate and uranium into our groundwater wells. Fall, organic matter decay. Decaying leaves and other organic matter fall into waterways, releasing nutrients and compounds. This can change the water's chemistry, making it cloudy and altering the taste. Nutrient imbalance, the breakdown of organic debris, can lead to an imbalance of minerals and nutrients in water system. As we move through these seasons from winter to spring to summer and fall, surface water bodies like lakes can experience a phenomena called thermal stratification, where in the winter months you might have colder water on top and warmer water on the bottom of a lake, and in summer months warmer water on the top of a lake and colder water on the bottom. As we progress through these seasons and things change, lakes are often known to turn over or flip, as they're referred to, where the cold water then comes to the top and the warm water goes to the bottom. This phenomena releases all the nutrients that have amassed on the bottom of a lake into the intake system, causing taste and odor issues, chlorine decay, treatment program problems. There's just a myriad of issues that can occur as we migrate through the seasons collectively, as opposed to what we've articulated as what occurs in the winter spring, summer, and fall. Drinking water treatment uses various technologies to remove contaminants and produce safe, clean water. Conventional treatment in municipal plants typically involves a sequence of steps, including coagulation, flocculation, sedimentation, filtration, and disinfection. Advanced treatment technologies are used for specific contaminants or when treating water challenged with sources like seawater. All of these processes involve the addition of chemicals for the ultimate removal of those compounds, whether they're coagulated together or they're enhanced for separation in advanced water treatment processes. Each chemical has its own impact on the ultimate building water system treatment, as well as the seasonality we've just discussed. Let's talk about conventional treatment technologies. Most municipal water treatment facilities use a multi-stage process: coagulation and flocculation. Chemical coagulants with a positive charge, like aluminum or iron salts, are added to the water to neutralize the negatively charged fine suspended particles such as dirt, organic matter, and some pathogens. This causes the particles to bind together, the flocculation process, into larger, heavier clumps called floc. Sedimentation: in this process, the flocks are heavy enough to settle to the bottom of a settling tank due to gravity, allowing the clear water above to be removed and the cloudy flocculated water to accumulate on the bottom. The clear water then goes into filtration. The water then passes through various filters, typically layers of sand, gravel, or activated carbon. These filters trap smaller particles, organic matter, and some microorganisms that did not settle during sedimentation. In some filters, the granular activated carbon can actually be experiencing a biological process that is positive to the treatment process, in that the organic material entering the porous spaces available to it on the activated carbon will then be consumed by good bacteria, allowing more space to be developed on that activated carbon for additional flocculants to come into it, be trapped, and removed from the drinking water. Disinfection. This is the final and critical step that kills any remaining disease-causing organisms or pathogens using disinfectants like chlorine, chloramine, or ultraviolet light. Also, ozone may be deployed, which is generated. Ozone and ultraviolet light do not leave a residual disinfectant. Residual disinfectant is often only maintained in the water as it travels through the pipes, ensuring a safety component from recontamination. Residuals can only be maintained by chlorine or chloramine. UV light immediately dissipates, and ozone only lasts a mere minute to allow for the disease causing organisms or pathogens to be killed. Now let's talk about advanced and specialized technologies. For specialized contaminants, we're talking about issues of water reuse or desalination. More specified technologies are employed. Membrane filtration. High-pressure membrane processes physically remove contaminants by forcing water through a semi-permeable membrane with tiny pores. So microfiltration, or MF, or ultrafiltration remove particles, bacteria, and viruses. Nanofiltration and reverse osmosis remove a wide range not only of dissolved substances, but it can remove salts, heavy metals, inorganic contaminants, including the forever chemicals or the perfluorinated PFAS that we discussed earlier. Reverse osmosis is often used for desalination, turning seawater into drinking water. Adsorption, not absorption, but adsorption, adsorbs materials into granular activated carbon, which are highly porous and adsorptive contaminants into their surface, effectively removing the taste and odor compounds, naturally occurring organic material, and synthetic organic chemical. Aeration is a process that transfers volatile organic compounds, VOCs, or hydrogen sulfide, from the water into the air, improving the health and safety of the water, as well as tastes and odors. Ion exchange is a process where water passes through a bed of synthetic resin that exchanges harmfully charged contaminants with more innocuous ions. This is useful for removing contaminants like arsenic, hexavalent chromium, nitrate, and the perfluorinated compounds. Biological treatment processes use indigenous bacteria within a media bed, as was discussed with the granular activated carbon, to break down and remove specific contaminants like nitrate and perchlorate. Advanced oxidation processes, AOPs, are processes that use UV light in combination with chemicals like hydrogen peroxide or ozone to generate hydroxyl radicals which destroy difficult to treat organic micropollutants such as pesticides and industrial solvents. The most common being 1,4-dioxane, which we're hearing a lot about in the press today. Let's move on to transmission and distribution of water after it's left the treatment plant. Drinking water quality during transmission and distribution is affected by several factors, including microbial growth, chemical changes, pipe material degradation, as an example, microplastic corrosion, and the overall integrity of the distribution system. Water leaving a treatment plant can deteriorate in quality before reaching the consumer if the system is not well maintained. Some of the concerns with distribution involve microbiological quality. While water leaving a treatment plant is essentially free of disease-causing pathogens, it is not sterile. The distribution system, pipes, valves, and storage tanks, can become a site for microbial growth, particularly in biofilms on pipe walls. Maintaining a sufficient disinfectant residual, as an example, chlorine or chloramine, and ensuring biological stability are crucial control measures. Monitoring for indicator organisms like total coliform help assess the biological integrity of the system. It's important to recognize that coliform are actually harmless, but they are the indicator organisms for regulatory authority from the U.S. Environmental Protection Agency. It is presumed that if coliforms are absent from the water supply, that the harmful pathogens like E. coli might not be present. We are learning through science that dangerous bacteria like Legionella can occur in the absence of coliform. So while we continue to use this as an indicator organism, we are migrating towards actually speciating E. coli and Legionella in conjunction with total coliform. Chemical changes. In the transmission and distribution of water, disinfection byproducts are formed. These DBPs, disinfectants like chlorine, react with natural organic matter in the water to form DBPs, which pose health risks upon chronic exposure. Monitoring DBPs in water distribution systems is required by a regulation at the EPA called the Stage 1 and Stage 2 disinfectants and disinfection byproduct rules. These are under constant review, and presently we are engaged in a 6-year review that will add additional components for monitoring disinfection byproducts that are formed with chloramination, as chloramination is newer as a disinfectant than what's been used for decades, the regular free chlorine. These types of disinfectants both form disinfection byproducts, but currently only the chlorinated disinfection byproducts are regulated. We're concerned with corrosion in the transmission and distribution of drinking water. Chemically aggressive or corrosive water can cause metal pipes to deteriorate, i.e., cast iron and galvanized pipes, leading to contamination by releasing lead, iron, or other metals into the water. Corrosion also facilitates biofilm growth and can degrade over time and release into the drinking water supply. Facilities with biofilm growth reduce the effectiveness of the disinfectants. Many drinking water utilities have migrated to chloramination. Chloraminated transmission systems can experience nitrification, where the bacteria or biofilm that have formed in the distribution system actually degrade the chlorine and allow for free nitrogen to express itself in the water distribution system. This free nitrogen or nitrification is a biological process. So corrosion can actually occur in a chemical process, but also a biological process. Many homes throughout the United States are plumbed with copper pipe. Copper pipe is very, very subject to biological corrosion or microbial induced corrosion. Completely different type of corrosion than we experience with chemical corrosive water that's usually affected by temperature or pH of the water. Another concern of the chemical changes associated with microplastics. Aging plastic pipe, PVC or PE, can degrade over time and release microplastics and nanoplastics into the drinking water, which is an emerging contaminant of water quality concern. Let's talk about the physical integrity and operational issues with the distribution system. One of the primary concerns is water age. The longer water remains in the pipes or in the system, the more the disinfectant residual decreases, increasing the potential for bacteriological regrowth and disinfection byproduct formation. Low velocity flow and dead ends significantly contribute to water age. Pressure through water leaks or transient hydraulic changes in the distribution system, negative pressure inside the pipes are lower than the outside, can draw external contaminants into the pipes from soil or other contaminants into the water system, especially during main breaks or repairs. We're also very concerned with cross connection, which is an improper or uncontrolled connection between a potable water line and a non-potable water source, which are significant contamination risks out in the community drinking water systems transmission and distribution. It's also a significant problem once we get inside the building. Let's move on and begin talking about storage. So we've talked about water is sourced, water is then treated, water is then transmitted or distributed, and it is stored in storage tanks. Drinking water quality in a storage reservoir is a critical public health concern. It's primarily affected to water age or stagnation, contamination risks from compromised physical barriers, biofilm, and sediment accumulation in the storage reservoir can affect chemical changes, biological changes, physical changes. Maintaining water quality requires robust management, regular inspection, and appropriate infrastructure design. So many reservoirs in this country have been designed with common inlets and outlets, without baffles or mixers. And what happens is the tanks will stratify. Much like a lake, a reservoir or a storage tank can experience thermal stratification. It can experience reservoir short circuiting, where the water comes in, passes by all the water that becomes stagnant, and goes right out of the drinking water reservoir. This is what we mean when we talk about appropriate infrastructure design. Let's begin by talking about water age and stagnation. This is arguably the most important factor in water quality deterioration in storage facilities. Longer detention times can lead to reduced disinfectant residuals like chlorine, which are consumed over time and encourages microbial growth. Disinfection byproducts. Formation is increased, and the contact between disinfectants and organic matter can lead to higher DBP formation. As an example, trihalomethanes and allocytic acids, which have potential long-term health effects. And finally, as we've discussed numerous times, in the system, nitrification using chloramines as a disinfectant residual during stagnation and warmer temperatures lead to nitrification events, forming nitrite and nitrate, both toxins in and of themselves, but also rapid biofilm regrowth. We're interested in contamination and physical integrity of the storage facility. Storage facilities are susceptible to external contamination if the physical barriers are compromised. Structural breaches like gaps or cracks or broken vent screens, open access hatches can allow for external entry of contaminants like animal wastes, insects, or bacteria. Open reservoirs, storing treated drinking water in an open reservoir poses a health risk of contamination from animal wastes, fecal matter, and other pollutants, potentially leading to outbreaks of pathogens like E. coli or Salmonella. Throughout my career, I've experienced many what I would characterize as surprises in water storage facilities. It's one thing to find dead possums or domestic cats or those where they are able to get into the screens, they get into the water, they die, they influence bacteriological growth. There's just all kinds of problems associated with it. Things like the common garden snail are actually airborne and can go through those vents and create a major outbreak of a snail colony within a drinking water reservoir, ultimately turning bacteriological and informing all kinds of water quality problems within a drinking water reservoir. And as we just discussed, open water reservoirs. People think that that's, probably not that common. Water's always stored in closed tanks. The cities of Los Angeles and New York actually store water in open water reservoirs. Many of you may recall on the news the city of Los Angeles has covered its exposed drinking water reservoir with millions of 3-inch black balls to cause the reservoir to sort of be covered, but that drinking water reservoir is in fact open to the air, open to airborne exposure, open to wild animals, open to birds, rodents. It's quite amazing that our two largest cities in this nation use open, uncontrolled drinking water reservoirs. Biofilm and sediment accumulation are quintessential conditions that promote the settling of particles and corrosion products, creating sediment layers at the bottom of a tank. Sediment accumulation provides for a safe harbor for nutrient sources and pathogen growth. Legionella is a prime example of a pathogen that can grow in these nutrient sources within a storage reservoir. This increases in disinfectant demand, and if they're chloraminated, the disinfectant chlorine is lost, free nitrogen is produced. We just get into a spiral condition, leaving the drinking water reservoir completely unprotected. This can cause turbidity problems, and if there's a hydraulic shift in the distribution system, this turbidity becomes disturbed and goes out into the building water system. Inside drinking water reservoirs, we're also concerned with algae and nutrient loading. With raw water reservoirs prior to treatment, we're often concerned with significant water quality problems due to increased nutrient loads, phosphorus and nitrogen, which lead to the harmful algae blooms that produce these cyanotoxins and compound causing taste and odor, geosmin or MIB in drinking water. The issue associated with the microcystins that are produced with a hazardous algae bloom, the cyanotoxins, they can actually continue to pass through the water and become a significant problem in a building water system. Finally, we're concerned with corrosion and material leaching. Aging tanks, especially those with old coatings like lead paint or grease, can leach out those toxic chemicals or provide food sources for bacteria in the water. The type of storage material, i.e., concrete, steel, or different types of plastic liners, can influence microbial regrowth and the water chemistry. Now that we've looked at the community drinking water system, source water quality, water treatment technologies, transmission and storage of that water, we need to be concerned with it entering the building and supplemental treatment that might be deployed by a building owner or operator. Building owners are ultimately responsible for maintaining the water quality within their properties and may need to install supplemental treatment systems to address specific water quality concerns and water quality issues not fully managed by the community drinking water system or municipal supply. While public water systems must meet EPA standards, water quality can degrade within a building's internal plumbing. Building owners' responsibilities include the maintenance of the plumbing system. Building owners are responsible for proactively maintaining their internal plumbing systems to minimize water stagnation, corrosion, microbial growth, such as Legionella bacteria, within the building owner's plumbing system. Just like a community drinking water system, buildings have storage areas, they have dead ends, they have places where water becomes stagnant within the building that not only lead to microbial growth, but can lead to corrosion and can ultimately lead to transmission of significant disease. We need to monitor these systems, and these are important building owner responsibilities. While not always required by federal standards for testing contaminants like lead and copper and bacteria, it is a best practice, especially after prolonged building closures. Oftentimes, work hour structures have been changed, leaving buildings closed from Friday to Monday. Long weekends, rotating schedules, people working from home have impacted the prolonged building closure process. When reopening a building after a long weekend, if certain flushing of that building needs to take place to make sure that any corrosion that occurred over the closure or any bacteria growth gets flushed out of that system. Domestic water systems providing water to a building in many jurisdictions, the owners of like rental properties, trailer parks with private wells are required to provide safe drinking water to the residents. And if tests show contaminants exceed these standards, they are treated just like a community drinking water system. Some of the supplemental treatment options available to building owners. If tests reveal specific water quality concerns, building owners may need to install supplemental point of use or point of entry treatment systems. The appropriate system depends on the identified contaminants, and it can include filtration with activated carbon filters or activated alumina filters, can remove a wide range of organic and inorganic contaminants, odors, and tastes. Supplemental disinfection, methods like chloramination, chlorination, ultraviolet light, ozone generation. All of these UV radiation can kill pathogens within a building water system. Some building owners have employed reverse osmosis. This process can remove a wide array of contaminants, including metals associated with corrosion as the water travels throughout the building, or other various chemicals that we've discussed can come from the community drinking water system as a result of treatment, distribution, and storage. Ion exchange or water softening equipment address hardness and specific inorganic contaminants like nitrates or other contaminants that might impact water quality from corrosion or microbial regrowth in the distribution system. Some of the key considerations for building owners include professional consultation, which is critical for building owners to consult with a water treatment professional to identify specific types of treatment needed for specific building applications and situations. Any supplemental treatment that occurs by a building owner in a water system requires certification. Certifications can be issued by the agency having jurisdiction for a community drinking water system, which might include the American Water Works Association, the Association of Water Treaters. ASHRAE, I believe, has certification programs that are recognized that can ensure the performance of standards for contaminants of concern. Proper maintenance of the water treatment equipment is extremely important, but if improperly maintained, these treatment systems can become ineffective or worse, have an impact on water quality that could actually be more dangerous than if you'd employed no treatment technique whatsoever. Routine maintenance is essential. Too many building owners put this equipment in, fail to maintain it, and it actually becomes more dangerous over time. Let's talk about use of water in a building and how its exposure to building occupants can affect their health. Buildings or premises water quality control concerns primarily stem from the degradation of water within the internal plumbing system after it enters the property line. This is often due to low or no water usage, stagnation, which allows for the growth of pathogens and the leaching of metals from pipes, fixtures, and appliances. Let's begin by discussing microbial growth or regrowth. Stagnant water in building pipes and fixtures can reach temperatures that are ideal for bacterial growth. The water coming in from a community drinking water system often is at a lower temperature, it's down below grade, it's cooler, but when it enters a building where there's adjustment for indoor air comfort can impact the water temperature in the pipes. This adjustment of water temperature hits that sweet spot where bacteria like to grow in plumbing systems. Legionella, the most common cause of waterborne disease outbreaks in the United States, is caused by this type of experience with warming water in plumbing systems. Legionella can cause a severe form of pneumonia, Legionnaire's disease, through the inhalation of contaminated aerosol from showers or hot tubs. It's important to understand that aerosolization comes from a sink. The aerator in the sink sprays mist up on your face when you're washing your hands or even washing your face or brushing your teeth. And those particles inhaled are what cause the disease. There's other opportunistic pathogens that get into water, like Pseudomonas or Microbacterium or E. coli. Oftentimes, these bacteriological exposures in building water systems can be fatal. It's important to understand that they grow in low flow conditions and biofilm inside pipes, waiting for their opportunity to expose a building inhabitant. Let's move on to chemical contamination. The loss of disinfectant residual, as an example, chlorine or chloramine, during stagnation reduces the water's protective qualities and allows other issues to arise. Lead and copper leaching from stagnant water, increased by the corrosion of pipes that can either be chemically induced or biologically induced, will corrode the fittings, leading to elevated levels of heavy metals in the drinking water, which can have chronic health effects. Disinfection byproducts. These can form as disinfectants react with organic matter in the pipes over time. This is also a major indoor air concern. Much like we can expose ourselves biologically to the inhalation of dangerous pathogens like Legionella, we can actually inhale the disinfection byproducts. Trihalomethanes and halocytic acids are volatile organic compounds. When we enter a shower and we smell chlorine, chlorine in clean water, free of organic matter, does not have an odor. What we smell is, in fact, disinfection byproducts. As systems become uh, exposed to nitrification associated with the decay of chlorine, oftentimes drinking water utilities will increase the chlorine dose to get away from nitrification. And it's that increase that then reacts with the organics in drinking water, causing that increase in chlorine smell of drinking water, actually exposing building occupants to indoor air quality from these VOCs. A building occupant washing his hands exposed to the air containing these contaminants can actually inhale more contaminants than they could in fact drink through consumption. Physical or aesthetic issues in building water systems include sediment buildup or accumulation of sediment in the pipes, which can lead to mechanical problems and failure promoting bacteriological growth. Shower heads often clog with this type of sediment accumulation. It is recommended that aerators on sinks be tapped out from the sediment that can accumulate in them, because these are areas where bacteria will stick onto those particles and regrow, not only causing the aerator in the sink to not work properly, or the shower head to become clogged, or the appliance to fail, but it's these areas where bacteriological growth can become very dangerous. These sediment also experience taste and odor and color changes, which change the aesthetic qualities regarding the most common water quality complaints and are often indicators of underlying chemical or microbial changes. And finally, cross connections. Improper plumbing connections, i.e., a garden hose left submerged in a chemical solution, or an air conditioning system connected to a potable water supply. In industrial settings, it runs the gamut on the levels of danger that can arise. But what happens is hazardous chemicals or contaminants are siphoned into the drinking water supply, causing illness and injury to building occupants. This is something that happens literally every day across America, where a building occupant may consume a dangerous toxic chemical that has siphoned into the building water system, having nothing to do with the community drinking water system, providing water to that facility. Let's talk about a building owner's management and responsibility. Water utilities are generally responsible for water quality up to the service line connection or meter. After that, the building owner is responsible for managing the premises plumbing system. The US EPA and the Centers for Disease Control recommend establishing a water management program, especially in larger facilities or healthcare facilities, to identify and mitigate risks. Mitigation strategies often involve routine maintenance, such as regular flushing of all water lines and fixtures to remove stagnant water and bring in fresh water with disinfectant residual, maintaining hot water temperatures high enough to kill Legionella above 60 degrees centigrade or 140 degrees Fahrenheit in the water heater. Oftentimes, hot water heaters begin to accumulate sediment. The gas is heating, or the electrical element is heating through that sludge, and then the temperatures begin to fall off, and you get into a warm or sweet spot where you'll actually begin to breed Legionella and other dangerous pathogens. Using mixing valves at the top of the water heater to prevent scalding. Replacing old filters in appliances like refrigerators or dishwashers. Some key strategies that building owners might want to employ are the development of the water management plan. This involves establishing a team and a plan to identify potential hazards establish control measures, monitor effectiveness, and document all activities. This program should be site-specific to the building owner's water system. We need to implement routine flushing, regular opening of taps, and run water, especially in infrequently used sections or dead legs of the plumbing system. This will help remove the stagnant water and bring in fresh water with adequate disinfectant residual. Flushing cold water lines first, then the hot water lines allow the material to be flushed into the water system, and then you hit the hot water system after that. It's the most effective approach. Flushing durations will vary, but generally involve running the water until the temperature stabilizes and any discolored water from sediment or air purging from the lines. We need to better control water temperature. Specific water temperatures in ranges that inhibit the growth of pathogens like Legionella are above the 140 degrees Fahrenheit, 60 degrees centigrade that we've discussed, but circulate hot water throughout the building at a minimum of 120 degrees Fahrenheit. Install thermostatic mixing valves at or near the point of use, faucets or shower heads, to prevent scalding while keeping the main system hot. Store and circulate cold water at temperatures below 68 degrees Fahrenheit or 20 degrees centigrade. This is difficult in low-lying areas like Florida or Louisiana or Southern California. Temperature of water in those buildings will exceed 68 degrees Fahrenheit, so extra care needs to be taken in those regions. Maintain system components, regularly inspect, clean, and maintain parts of the water system. Remove and clean faucet aerators and shower heads periodically to prevent scale and biofilm buildup. Drain and clean hot water tanks to remove accumulated sediment. Replace point-of-use filters, i.e. those we have in our refrigerators, ice makers, our faucets, according to the manufacturer's instructions, as they can remove disinfectants and harbor bacteria if not maintained. All too often, as I travel around the country, I look at ice machines in hotels, restaurants, hotels, hospitals, just places you go where you can see that they're readily available. And oftentimes they're 3, 5, 10 years old. These filters on these appliances have a life expectancy of 6 months to a year maximum. Even if they continue to have absorptive capacity, they have gone biological and can actually impact water quality significantly. At the same time, we need to focus on dead legs in the plumbing system, where water sits for long periods of time, accumulating biofilm and sediment, and ultimately have the ability to hydraulically shift and go back into areas of high use, significantly contaminating the building water system. Use point-of-use water treatment systems. Consider point-of-use filters in high-risk areas such as healthcare facilities to physically block pathogens from reaching the user in conjunction with a full water management plan. Automate and monitor for large or critical facilities. Consider smart water management systems that automate control measures and allow for continuous monitoring of parameters like temperature and disinfectant levels. And finally, and perhaps most importantly, communicate with building occupants. Notify building occupants about the status of the water system, water quality, and any necessary flushing programs. It's important that building occupants have an appreciation for the source to tap parameters that we've discussed today. It's important that building owners and people that are involved in the water management plan engage and actively work with the water management program. And in that, communicate the impacts to the building occupants. Everyone wins in this scenario. Thank you for joining me today. I hope these subjects have helped you better understand how water impacts occupants' health and safety.